we begin our discussion on enzyme kinetics. We will cover this in 2 lectures, and what we need to understand from this is what we mean by enzymes, what we mean by enzyme catalysis, enzyme mechanisms, and what are the specific features of enzymes. Now, if we consider what enzymes actually are, they are the backbones, the pillars of any biochemical process. Any biochemical process occurs through these enzyme reactions. So, when we consider enzymes in general, what we will study in this particular lecture is the enzymes as catalysts, the different types of enzymes, and enzyme kinetics in general. When we look at what enzymes are, these are protein catalysts, which means that they alter the rate of a chemical reaction, in this case a biochemical reaction, that will occur without a predominant change in the structure of the enzyme, which we will see as we go along. So, if we have a general set where we are looking at a reactant going to a set of product, and we have a certain activation barrier that has to be crossed. We know that when we have enzymes, if we have an uncatalyzed reaction, this is what we have, and if we have a catalyzed reaction, we know that we have a reduction in the activation energy. This is exactly what enzymes also do when they act as protein catalysts. In the enzymes, we have what is called an active site, something that we will see later on, and we have amino acid residues in this active site, because we have to remember that this enzyme is a protein, and the important properties that this active site has is its charge, its pKa, a specific hydrophobicity, flexibility, and a definite reactivity for the biochemical reaction to go on. There can be simple enzymes. These simple enzymes are composed of whole proteins. The complex enzymes will be composed of the protein, but in addition to this, it can have what is called a prosthetic group or a cofactor, or it might need even a metal for its activity or its enzyme catalytic activity to be complete. So, we have what is called a holoenzyme, an apoenzyme, or a prosthetic group plus the coenzyme. The prosthetic group is a small organic molecule that is bound to the apoenzyme by covalent bonds. When the binding between the apoenzyme and the non-protein component is non-covalent, this is called a coenzyme. Now, what happens in enzyme reactions is it may so happen that the enzyme requires this prosthetic group or the coenzyme or even a metal for the reaction to be complete, for the reaction to go forward. The different classes of enzymes are oxidoreductases, transferases, hydrolases, lyases, isomerases, and ligases. So, these are the 6 different types of enzymes that catalyze specific reactions. So, if we were to add water across a hydrogen bond resulting in hydrolysis, this would be a hydrolase. If we are transferring a specific functional group, a chemical group between donor and acceptor molecules, we would have a transferase. And if that transferred moiety, the chemical moiety that is being transferred happens to be a phosphate, this is called a kinase. If we have ligase, that means we are linking 2 different chemical groups together. If it is an isomerase, it is an isomerization reaction. If it is an oxidoreductase, it is the addition or the removal of hydrogen atoms, or an oxidation reduction reaction. So, these are the specific definite types of enzyme classifications that are present. When we look at enzyme characteristics, they accelerate the reactions, as we saw, by lowering the free energy of activation. They often bind to the transition state of the reaction better than the substrate, and they exhibit what is called saturation kinetics. We will see what that means in a moment, and they work at an optimum temperature and an optimum pH. We have to remember that these enzymes being proteins, any extreme of pH we learnt will denature the protein, any extremes of temperature will also have an effect on the protein structure, which in turn will affect the enzyme active site, and the specific catalytic reaction or the enzymatic activity, the enzymatic ability will be lost. So, the catalytic activity is defined or is rather measured in terms of what is called a turnover number. What do we mean by this? It is the maximum number of moles of substrate that can be converted to product per mole of catalytic site per second. In the Michaelis-Menten kinetics, we will not go into the complete details or work out this kinetics because this is something you have done previously. We have to remember, or we have to just understand the methodologies or the features associated with Michaelis-Menten kinetics. The first idea that we have to have is that the enzyme has an active site. This active site binds a substrate. When it binds a substrate, it forms what is called an enzyme substrate complex. This enzyme substrate complex then dissociates to regenerate the enzyme and give a product. Now, this enzyme is again ready to take in another substrate. So, we have an enzyme substrate complex formed in what is called a pre-equilibrium reaction. The rate constant for the forward reaction is K1, the reverse is K minus 1. Once this ES complex is formed, it dissociates to form the E plus P. So, the specific features here are we assume the formation of an enzyme substrate complex, and it assumes that the ES complex is in rapid equilibrium with the free enzyme. The breakdown of the enzyme substrate complex now to form products is assumed to be slower than the formation of the ES as well as the breakdown of the ES to reform E and S. In the reaction scheme that we just learnt, we can apply what is called a steady state approximation to the ES complex. What do we mean by this? We look at the rate of formation and the rate of destruction of the enzyme substrate complex. This means that where the forward reaction is the only way by which the enzyme substrate can be formed, and the decay can occur through either K minus 1 or K2. If we now work out some algebra based on enzyme kinetics, we will come up with what is called the Michaelis-Menten equation. The Michaelis-Menten equation tells us that this reaction has a certain velocity to it. What do we mean by this velocity? It is the formation of the products or the decrease of the reactants, or in this case the substrate, because we have a specific conversion reaction. Any kinetics is associated with a reactant to product. And how do we monitor this? We monitor this either by the depletion of the reactant or the formation of the product. And we would have specific methodologies to look at this. If we have, say, a pH, a hydrogen or a proton formation or reduction, we can monitor this through pH. If we have an absorbance, if we have a color change, we can use spectroscopy, which is by far the most widely used method to look at enzyme kinetics. Now, what we have here is we have a term called Vm. This is the maximum velocity possible, and it considers the total enzyme concentration, which means that if all the enzyme were to be converted into the product through the K2 step, we would have the Vmax. This Km quantity is known as the Michaelis-Menten constant. This constant, you can see, is a measure of the K minus 1, the K2 by the K1. What is the K minus 1 and the K2? These are where the enzyme substrate complex is disintegrated or it is destroyed, but the K1 is where it is formed. The V, as we said, is a formation of the product with time, and it is the Kcat, the catalytic rate constant, with the ES, that is the enzyme substrate complex. Now, what can we measure? Because this is extremely important when we are trying to understand what we can do. Since being an experimentalist, you will know whether you can measure the enzyme as the reaction is going on, whether you can measure the substrate. Since you added the substrate to the solution or to your experimental setup, you know how much substrate you have added. You know how much product is being formed, and what you do know is you know the total amount of enzyme that you have added. Part of this enzyme is going to be in the free form, part of it is going to be in the enzyme substrate complex form. So, the total enzyme concentration is going to be the free enzyme plus the enzyme that has gone into form the ES complex. So, this is where we have the total enzyme that is equal to the free enzyme plus the ES complex. So, if we have a measure to understand how much free enzyme is present or how much ES complex is formed, then since we know any one of these, if we know any one of these, then we know the other one, because we know the total amount of enzyme that we have started off with. So, we consider what is called a steady state, as I just mentioned, and we can get what is called the Michaelis-Menten constant. So, the features assume that we have this, as we mentioned before, the formation of the enzyme substrate complex, the breakdown, and a specific Michaelis-Menten kinetics given by an expression. So, we have what is called here. So, this is the substrate concentration and this is the velocity of the reaction, the initial velocity of the reaction. So, as we increase the substrate concentration, there are certain features that we have to look at in this graph. There is an initial velocity that is taken by this tangential part from the hyperbolic curve that we get here. There is a plateau or a saturation kinetics attained. Why is this? We have to remember that the enzyme is a protein. It has an active site to it. So, there is a limit to the number of substrate molecules this active site can hold. So, however much we increase the substrate concentration, it will reach a maximum when all the active sites of all the enzyme molecules present in the solution have been filled up. But what do we see in terms of kinetics in the initial part? We see that low substrate concentrations, we have the V proportional to the S, following first order kinetics. But as we have a higher substrate concentration, V is independent of S. There is no change in the velocity. We can reach a V max and it is 0 order. And what do we have here? If this is the V max value, half of the V max based on the Michaelis-Menten equation, the expression relates to the Km. So, the substrate concentration at which half the maximum velocity is attained is equal to the Michaelis-Menten constant. So, we have the kinetics and we have certain terminologies here that we have to look at. So, we have what is called, if we look at this reaction, the pre-equilibrium reaction, the E plus S forming the ES complex. This is an equilibrium constant associated with the equilibrium concentration of the enzyme substrate complex, the E and the S. This is what is called an association constant. So, it is an equilibrium association constant and we can see that the units here are mole inverse. If we take the reverse of this, we will have what is called a dissociation constant, which is ES by the ES complex, and the units here are mole. This will be something that you will also study when you look at protein ligand binding, where we will have association and specific binding constants associated with your reaction. Now, when we have tight binding, it means that we are looking at a low dissociation. A tight binding means that the ES complex concentration is high. If this is high, Kd is low. So, if we want tight binding, we want to look for a low Kd and a high association constant. What does this mean? Now, when we have an enzyme substrate complex form, it has to be a very delicate balance. We do not want the substrate to bind too tightly, because then the equilibrium will be shifted only to one direction. We have to have an equilibrium where because the enzyme has to be free and bind the substrate, it has to be a relatively loose non-covalent binding in most of the cases. There are covalent reactions that also occur, but we will see that the enzyme goes back to its initial stages to be ready to take up another substrate. So, if we have a specific turnover number, or let's look at this. So, we have, for the initial substrate concentration, we look at an S0 that is much greater than the total enzyme concentration. What does this mean? It means that we can make certain approximations. The certain approximations will allow us to calculate the initial rate of the reaction, which will help us in determining what the Michaelis constant is. Now, the Kcat is a value that gives us a direct measure of the conversion of the substrate to the product. It is the number of substrate molecules turned over per enzyme molecule per second, and the overall rate of a reaction, just like any kinetic reaction, is limited by its slowest step, the rate determining step. In this case, the Kcat will be equal to the rate constant, and for the Michaelis-Menten system, this is K2, where we have K2 Es going to E plus P. So, we have the turnover number, which is defined as the Vmax by the Et, the total concentration of the enzyme present, and the Km value that we have, the Michaelis-Menten constant, is a useful indicator of the affinity of an enzyme for the substrate. If we have a low Km, we have high affinity, and then if we have a high Kcat by Km ratio, this implies it is an efficient enzyme. It will work better in terms of having either a large Kcat or a small Km. Now, how do we measure all this? How do we calculate all this? This is given by what is called a Lineweaver-Burke plot, where if we look at the Michaelis-Menten kinetics, we look at a graph where we have a hyperbolic curve. It is very difficult in that case to determine the actual value of the Vmax, because we do not know where the Vmax will or at what velocity it will be attained. So, in this case, we have, if we rearrange the equation and we plot what is called a double reciprocal plot, where we have 1 by V versus 1 by substrate concentration, this can be a straight line, as you can see from the expression here. And what we have here is the y-intercept here is 1 by Vmax, and the intercept on the x-axis is minus 1 by Km. So, we straight away get the values of Vmax and Km, the Michaelis constant, as well as the maximum velocity attained from this double reciprocal Lineweaver-Burke plot. There are other plots also that can give you the Vmax and the Km. Another common plot is the Edey-Hofstee plot, but the Lineweaver-Burke plot is something that is used more often for enzyme kinetics, and this will be demonstrated to you in the experimental part of this lecture. There are other ways in which we have certain reactions. Some are called bi-substrate reactions. What do we mean by that? We can have two substrates. If we have two substrates, then how does this work? It means we have S1 and S2, and we can have two products. Suppose we have a reaction like this, where we have Ax plus B, and X is transferred to B from A in a transferase reaction. There can be sequential binding of S1 and S2, random substrate or ordered substrate. This will depend upon the active site. It may so happen that if it is a random substrate binding, it would not matter whether S1 bound first or S2 bound first. But in an ordered substrate binding, it would mean that S1 would have to bind first before S2 can bind. This may result in some variation in the enzyme structure, which we will see later on. In the ping pong reaction, S1 has to bind first, P1 has to be released, then because the enzyme has a different structure, then the different enzyme, let us call it enzyme E prime, will then bind S2, form P2, and then go back to its original formation. If we look at what an enzyme active site is, I have been talking about the enzyme active site. This is the area of the enzyme that binds the substrate. The structure has a unique geometric shape that is designed to fit the molecular shape of the substrate. So, there is a shape complementarity in addition to a chemical complementarity for the addition. Each substrate is extremely substrate specific. Each enzyme is very substrate specific. So, the active site is complementary to the geometric shape of the molecule. If we look at this geometrical shape, we will look at the mechanism of this specificity. This is ribonuclease A, and we will see how the shape has been defined or realized, or how it is actually shaped to bind the substrate. So, let us look at this. If this is our enzyme molecule, this is our active site, and this is our substrate. This is the enzyme substrate complex, where we have the binding of this small molecule to the active site of the enzyme for a particular reaction to occur. So, we have substrate binding specificity, geometric, electronic, stereospecificity, And the binding to the active site is defined by two different methodologies, either a lock and key model, like we fit a key to a specific lock, or an induced fit model. What happens is, in both cases an enzyme substrate complex is formed, then there are specific bonds that are formed or broken, and the products are released. Let us look at these two different types. One is the lock and key model. In this site, where we have the active site of the protein, the enzyme binds a substrate in a region called this active site, and we learned that there are only certain substrates that will be able to fit the active site, which means that if we have a circular substrate, it is not going to fit in the active site here. The substrate is shaped like this, it fits into the active site of the enzyme perfectly, and the amino acid groups that are present here will fit in the substrate in a manner that allows for chemical complementarity as well. And then once we have the product formation, then we have the enzyme back to its original form, which can bind the next molecule of the substrate. If we look at the induced fit model, in this case the enzyme structure is flexible, it is not rigid like in the previous case, and the active site will adjust its shape in such a manner so that it can bind the substrate in a manner which will allow for the catalytic reaction to occur. This increases the range of substrate specificity, and there are shape changes that occur that improve the catalysis during the reaction, and there are specific transition state like configurations that occur. So, if we have a specific active sites that are shaped like this, we have the substrate that can come in, and what you can see is the enzyme has modified itself or adjusted itself to accommodate for the substrate that is also being a chemical component, it can adjust itself, it will have changes in bond formation, and then we have the product formation. So, we have what is called a lock and key method, we have what is called an induced fit method. So, these are the two models that are usually used for enzyme reactions. We have given here two references, one referring to the biochemistry book by Voigt and Voigt, and another very good book about enzyme kinetics, which gives you various reactions that can occur. Because what we just looked at is, we just looked at a simplistic method where we have the enzyme and the substrate bind together to form the enzyme substrate complex. Now, we understood that the enzymes are biological catalysts. What does this mean? This means that there is an active site, there is a transition state, there is an activation energy. Now, when this activation energy is reduced, like in any kinetic reaction, we have a catalyst present. In this case, our catalyst is an enzyme, the reaction is a biochemical reaction, and the enzyme is a protein. When the enzyme is a protein, the protein can act by itself if it is a simple enzyme. If it is a complex enzyme, in addition to the apoenzyme or in addition to the enzyme itself, it will have or it will require a prosthetic group or a coenzyme or even a metal ion for its catalytic reaction to occur. The active site is lined by amino acid residues that have specific characteristics. We learnt of the different types of amino acid residues that can, some of these will line the active site, and we will see that there are a large number of histidines actually that are present. And this is because the pKa value of the histidines, as I mentioned earlier in one of the classes, is in such a range that it matches with their physiological pH. We have the binding that occurs to the active site through complementarity. What kind of complementarity? Either geometric or chemical complementarity. So, if we have a hydrophobic active site, if we have an acidic active site, if we have a basic active site, or if we have that can form aromatic pi stacking or different types of interactions or hydrogen bonding. We want to have a non-covalent interaction between the enzyme active site and the substrate. And what is going to happen? The enzyme substrate complex is going to form, and this is then going to release the product in a specific reaction. Now, when the product is released, there are two models that are followed, the lock and key model and the induced fit model, that will tell us whether we have our enzyme reaction occur in a manner that can be monitored, and we will see a specific enzyme reaction when the experiment is done in the experimental part, and then we will look at other activities of enzymes. Thank you.